Headphones. They may appear to be, on the surface, the least hardest device to drive. Well, in actual fact, they are kind of the most difficult device to drive. Stick around and we'll discuss this topic a little bit more in detail. Greetings, the Astro 30 here, and welcome to a brand new video. Today I'm going to be discussing driving a pair of run-of-the-mill headphones like that. Now, the impedance of these headphones, which is kind of important, is around 64 ohm. Now, when I say headphones are the most difficult device to drive, well, speakers in general are the most difficult device to drive. They're not the easiest in the world. However, headphones can be considered difficult because not all headphones are the same. They're not all the same impedance. We have 32 ohm, 64, 120, 160, 180 ohm, etc. And the more expensive a headphone you buy, the chances are it's going to be a fairly high impedance. Now, a normal power amplifier does not like driving high impedance loads. That's just the way things are. And back in the old days, say in the late 70s, early 80s, a lot of headphones were just 8 ohms. They were just little tiny 54mm quarter-inch drivers. Something similar to that, but obviously a lot smaller. They weren't quite that big. But yeah, they were 8 ohm back in the day, and a lot of amplifier manufacturers, all they used to do was the headphone socket was wired through a dropping resistor directly off the output of the power amps. That was fine back then. These days, yeah, headphones have a higher impedance than they used to. And you really need a separate dedicated amplifier to drive the headphones, and that's going to be today's topic. So today we're going to be looking at an OpAmp based headphone amplifier. Now, this is not a new concept, and in fact this is very similar to the OpAmp based power amplifier video that I presented earlier, and I'll put a link in the description below to that video so you can check it out. The only difference is with this version we're using low-powered signal transistors as the output stage as compared to larger power transistors. The reason being is because we're not driving a speaker directly, we're driving a pair of headphones. And just remember, because headphones rest right at your ears, you're not going to want that much power going into the headphones because you will damage your hearing. Now, this circuit is a Class AB amplifier, and the heart of it is this NE5532. The reason I keep using NE5532s is because, well, I've got stacks of them, and they're a relatively rugged op-amp. There's nothing wrong with them. Over here we've got a BC337 NPN transistor going to the positive rail at the collector, and a BC327 with the collector going to the negative, and the two emitters join via these two 33 ohm resistors on the output, which form the output. Now, in this configuration, what we're looking at is what's known as an emitter-follower push-pull amplifier. And the reason we use emitter followers is because emitter followers allow you to go from a high impedance source to drive a lower impedance source. Now, headphones are a relatively low impedance source, so hence we use an emitter follower. Now, the two emitters here also are part of the feedback network of the op-amp. As we can see, we're going through this 2K2 ohm resistor back to pin 2, which is the inverting input of the 5532. This resistor and this resistor set the overall gain of the op-amp, which is around 3.2 or a gain in decibels of 10.1. We'll look a little bit into decibels a little bit later of how to calculate that figure and what it actually means. But at the output of the OpAmp pin 1, we're going through this self-biasing network which allows both of these transistors to be biased at class A, B or just above cutoff. And the reason we use these two diodes here is to try and minimize the crossover distortion in the output devices as much as possible. Now the reason we have these 33 ohm resistors here instead of connecting the emitters directly together to form an output is a bit of thermal stability here. Now as these devices start to heat up, if these diodes are in close proximity to these devices are going to start to heat up as well. And what happens when these devices start to heat up is they start to turn on the transistors slightly harder, which then ends up heating up these two output transistors a little more. And then conversely these start to heat up more, which then bias these transistors even harder, and etc. and so forth, and it just goes around in a big circle until the point where these transistors go kaboom and end up a molten mess on the circuit board. Once these transistors get fairly hot, there's no going back. They're basically going to be destroyed. So these two resistors here help to minimize the current flow through the transistors to try and minimize thermal runaway. This 68 ohm resistor here on the output serves two functions. The first function is in case this output is shorted to ground because it's connected between output and ground to the headphones. So it's not going to destroy these transistors instantly if this happens to be shorted to earth. However, if this was shorted to one of the power rails, is anyone's guess, but that should never happen. But in the event that this is suddenly brought to ground, i.e. you're plugging in a pair of headphones into the socket and the tip of the plug shorts between the ground and the right hand channel at the same time, which is quite common, you can end up damaging these output transistors quite quickly because these are only small signal transistors, remember, and they do not like being shorted at all. In fact, no transistor does. So effectively when this is shorted to ground, this is acting as a 68 ohm load across these transistors. So then the current path is going to go across this resistor rather than through the transistors. However, if this is just a normal quarter watt 68 ohm resistor, that's not going to last very long, but at least it'll save the transistors from damage. And the second purpose to this resistor is basically to isolate this circuit from the long lead of the headphones. In other words, it's the same as if you were connecting this up to another amplifier stage. You'd put in a little resistor here between the output of one stage and the input of the next, just to stop the first stage from going into oscillation. So on long cable runs, this will also help to prevent the thing going into oscillation, which is not what we want. And conversely, the 1K resistor over here is known as a stopper resistor, and it just stops any radio frequency interference being picked up at the input. So that's the whole circuit that we're going to be using today, and our test impedances are going to be 32 ohm, 68 ohm and 120 ohm respectively. Now I can't get these values, well, I can't get 32 ohm for a start. I can if I stick a 1200 ohm resistor in parallel with a 33 ohm, you get close to 32. I'm going to use a 33 ohm, it's only 1 ohm difference. My headphones are 64 ohm, I can only get E21 value of a 68 ohm, you know, it's 4 ohm difference. There's not much in it. But these are the test loads that I'm going to be powering into from this circuit to see if we get any difference in output power, which we should, and at the extreme end of 120 ohm, how much difference between that and 32 ohm there is. So that's going to be the order of today, and we're going to build up this little circuit on a piece of breadboard and test it out, and I'm going to plot out all the power outputs at a given input sensitivity. That's the other thing we've got to find out, is what is the input sensitivity of this before this thing starts to clip. And once we know that, we can then calculate our power outputs into the given loads and then come back with a final review. So let's do that. I farted. Okay, and the circuit is breadboarded up. I've got the USB based oscilloscope going. The yellow trace is what's coming at the input of the circuit, and the green trace will be what's at the output, and currently there's nothing because it's not turned on. Got the DDS set to 1 volt peak to peak 1 kilohertz, and the power supply set to around about plus minus 15.2 volt. So currently the output is not loaded. In other words, I haven't got a loading resistor across the output between that and ground. For now, I'm just going to test whether we have an output signal as soon as I apply power. And the green trace, both these traces are set to the same voltages per division of 1 volt, so we should see the green trace at least 3 times larger than the yellow trace as soon as I turn it on. Well, that's the theory anyway. Indeed we do. We look at that. So I did manage to get this oscilloscope to calibrate correctly, so it shows the voltages properly in this Open 6022BE version 1.0 beta PR18 software. And currently we're looking at a peak to peak voltage of 3.3 out. So we have a gain of roughly 3.2. Okay, so that's the preliminary test done. So let's actually load it down into some resistors. I'll start with 33 ohm and we'll do another test again. Okay, first off is the 33 ohm 5 watt resistor. So I've not changed any of the settings on the oscilloscope. We're still on both channels at 1 volt per division. Now I'll turn the load on, and immediately we can see that we've actually got pretty much the same output signal as the input signal. So driving into a 33 ohm load, we've actually got a reduction in gain of at least 3 times. So let's find out what the maximum input is before clipping. So I'll set my input voltage to 5 volt to start with. That's peak to peak, and immediately it's clipping. In fact, it's actually clipping at the input as well. So I'll drop it down till the clipping disappears. Right, the input's no longer clipping, and we're about 3 volt peak to peak. So the DDS's maximum output's about 3 volt. That's fine. So if I keep reducing the gain, there we go. Basically, we're at 2.3 volt in and we're getting 2.4 out. So we're not actually getting much amplification at all. So you can see immediately that driving a 33 ohm load, as in a pair of headphones, is a considerable bugger. Okay, so now let's change that to a 68 ohm. Okay, and the 68 ohm is now in its place. I've put the DDS's peak to peak voltage back to 1 volt. So now I'll turn the load on, and immediately we can see almost double. So at 1 volt in, we're getting roughly 1.6 out. So now I need to increase the input to find out its input sensitivity. So I want to see before the output starts to clip how much we're getting out. I'm currently pushing 2.4 in, and I don't see any signs of clipping yet. So we can see immediately driving a 68 ohm load or 64 ohm load speaker headphones is a lot easier than a 32 ohm. So I'll drop that voltage per division down to 2 volts so we can see it a bit better. Ah, there we go, we're starting to clip there. So I'm going to call it there. So our maximum input sensitivity is 2.8 volt peak to peak, and our output is 4.32 peak to peak. Actually, it started clipping again, I don't know why. Why is it doing that? Okay, now it's the 120 ohms turn. We're back down to 1 volt peak to peak input. Turn the load on. We're roughly getting double the output, so there's not much difference between 68 and 120. So I know that the input sensitivity for 68 ohm was 2.8 volt, so I've set it straight to 2.8 volt. And we're getting 5.7 out at the moment, so I'll keep on increasing the input till it clips. So it's really pushing it, so that's clipping there. We're at no clipping there, so I want to say 3.5 volt peak to peak in versus 7, about 6.9 out. Yeah, so we'll say 3.3 volt in versus 7 point something out. We'll just say 7 volt out. Now I'm just going to redo the 33 ohm load test because I forgot to write down the figures. Now I've left it run for a few minutes, and currently we've got 3.2 volt going in, and the output has sagged off to 2.6 because we can now see that it's starting to flat top, and that's just after it's been sitting there loaded down for a minute or so. So I'll turn the load back off and then back on, and it comes back up again. So that's an interesting phenomenon. I'm not 100% sure what's causing that, but anyway, I can't really go any higher than about 3.3 volt peak to peak because the input starts flat bottoming. So 3.2 is the max the DDS will do, and we're looking at an output of exactly what we're putting in. So 3.2 in, 3.2 out. So that's not much of an amplification. It's more of like a one-to-one buffer. So the conclusion is, yes, it will work as a headphone amplifier, but as I already stated in the beginning of this video, not all headphones are equal, and driving headphones can be a complete bugger. And well, we've just proved that. And as I'm talking, we can sort of see the output is starting to flat top slowly, and I'm not sure what exactly is causing that, and it does it on any load. It doesn't matter if it's 33, 68 or 120. So that could also be anything to do with the transistors going slightly out of linearity. So if I back it off to 2.2 volt, it's remaining okay, but it is still starting to flat top. We can see that it's still flat topping off, which is kind of strange. It shouldn't be doing that. So I'll put that back to 1 volt per division. That is bad and annoying. So I'll back it off even further. And no sooner have I backed it off, it will start flat topping again. So that's pretty strange. And the reason would be is because those transistors were getting hot. See, signal transistors do not work very well as power amplifiers, and that's what it's basically trying to do. Is the reason why we're seeing flat topping is because as these transistors heat up, the biasing starts to change. These diodes, which are in close proximity, as already explained, will start to heat up, which effectively turns these transistors on harder and harder and harder, and we start to get flat topping because, well, we're driving these transistors now into saturation. But of course, we'll work out what the powers are before that happens, but I'm pretty sure that's going to be pretty loud into the ears, and no one's going to have have the thing running that loud into your eardrums. So let's me do the calculations off screen and I'll come back with my results. And here is the results, and you're not going to like them. At 33 ohm we have a power output of 77 milliwatts at an input of 3.2 volt peak to peak. With 68 ohm loads we have 68 milliwatts, so we're actually about 9 milliwatts less in power than the 33 ohm counterpart here. But then we have an input sensitivity at 2.8 volt peak to peak. If we kept them at 3.2 all the way along, we'd have probably better valid response. We'd probably have more valid results. But yeah, so 68 milliwatt into a 68 ohm load, and at 120 ohm we have 102 milliwatts at 3.3 volt peak to peak input. So yeah, you can expect to get about 100 milliwatts out of that circuit, but just be aware that when these transistors start to heat up, they will start to clip rather badly. And I just redid the calculation on the 68 ohm load at 3.2 volt peak to peak input. We're looking more at like 91 milliwatts. But yeah, as we can see, it's not going to produce that much power. You could change the gain structure of that circuit to allow probably a less sensitive input. But remember, you can only push out as much as you can push out. You can't make it push out any more than, well, it's capable of doing. I also figured out why the DDS was clipping at 3.3 volt peak to peak, because there's an offset here, and that was set to 9.8 volt. I've set it back to what I remember it was by default when it was first turned on, which was about plus 2.5 volt, 2.8, something like that. And my signal is relatively clean. So if I change the amplitude now to 5 volt peak to peak, it's no longer clipping. So yeah, the offset was set wrong for a start. Oh, silly me. I knew that this DDS was capable of generating 10 point odd volt output before clipping, which is why I found it strange. So does that mean we should do the test again? Well, I don't see any point to it, but alright, I'll stick at 68 ohm load now, for now, and I'll turn the output on. And it is flat topping, but if I bring that back down till the clipping goes away, yeah, okay, we've got 6.4 out versus 4.2 in. And with the tests completed and done again, the results are a little bit more impressive, but not by much. We've got 103 milliwatts into 33 ohms at 3.7 volt peak to peak in, 150 milliwatts into 68 ohms at 4.2 volt peak to peak in, and 154 milliwatts into 120 ohms at 4.5 peak to peak. So yeah, there is a difference between 33 and 68, so we can imagine a difference in power output only by about 50 milliwatts or so between 32 ohms and 64, but not much in it between 68 and 120, or 64 and 100 and whatever it is, 120. But we can see you need to put a little bit more power into the circuit to get that power out again. And this is all clean power before clipping and before the transistors start to heat up too much to the point where they start going non-linear. So my conclusion is, yes, it works. Doesn't work all that great, but it does work and it does the job. It's not what I would call a high-end headphone amplifier, but it'll do the job. Now this circuit here actually comes from Silicon Chip magazine. It was, don't know who designed it. It was designed by either Leo Simpson, John Clark, not sure who, but it's been around since the early 90s. They've used this circuit countless number of times in different amplifier projects when they needed to power headphones. And it's if it works, why change it? Now the thing is, they were using TLO 71s and TLO 72s respectively. I'm using any 5532, but it shouldn't really make any difference. The only thing that does change between the different headphone circuits that they use is the values of the resistors and the gain. However, its bass remains the same, and they always use the 337 and the 327. They're roughly 680 milliwatt transistors each, so they are capable of driving headphones, but not to the point where they're blasting, because, well, as we saw on the scope, it starts to go very non-linear after a while, and it starts flat topping badly. Okay, so the next burning question is, what is its frequency response like? Well, it's going to be roughly the same as the frequency response of the NE5532 itself, because those transistors aren't going to add much in the way of its own characteristics or distortion on the output unless you're actually pushing high powers. Currently I'm at 1 volt in and getting roughly double out, so we're only about a third of the power and the transistors are mildly warm. So if we now go into sweep mode and have a look, we can see that it's remaining relatively stable at around 1.6 volt out, 1.1 in roughly, and it's not changing. So we're also going on the frequency response of the DDS as well, so keep that in mind. But overall the frequency response is good, so we can see without actually having to do a sound test. Something hit the roof real hard. Without having to do a sound test, because, well, we wouldn't hear anything because I'm not going to plug it into a speaker because it's not designed for that. But we can see from the frequency response that, yeah, it is slowly shrinking off a little bit, maybe, but it's remaining relatively flat, the whole response. See, this is what's happens. It's starting to fucking piss off. And after a while, the output signal has just gone to absolute shit. Even now to the point where the DSO can't even pick up what the frequency is coming out. And that's dropped off to 156 millivolt peak to peak, and it's getting smaller and smaller. And now the output has disappeared altogether. So that's fairly odd. I thought maybe it's because these transistors are getting too hot, but they're not. They're not even warm. And now we've got bugger all output. Well, I can't find the problem, but anyway, it's now unloaded on the output and it's not shrinking off. We're getting 3.2 out at 1 volt in. Maybe it is starting to drop off. It's made a liar of me. It's now dropping off completely. Well, that's interesting. So this is unloaded, so I don't know what is happening to the circuit, but this makes it a totally unusable amplifier, because if it's going to do that, you plug headphones in and all of a sudden the sound disappears. So I don't know whether I've got maybe a defunct IC. Yeah, so what I might do is I might change the IC and see what happens. Okay, it's not the IC, I've changed it, but I think I might know what the issue is. There's no biasing resistor, we'll say, on pin 3 to ground on this circuit. So that might be why it's disappearing off. So what I might do with it running still is I will take pin 3, which is our input, and bring that down to ground with a 22k resistor. And lo and behold, that was the issue. And now it's remaining fairly stable at 3.1 volt out. That's still unloaded, so I can load that amplifier back down with 68 ohm again, and we'll see a drop in voltage, yes. But we're still getting 1.5 out. I forgot basic OpAmps 101. OpAmps need, in bipolo, they need on their input a reference to ground for them to operate correctly. As the circuit was drawn, it was actually taken out of that guitar preamp that I built, and you'll probably find the input pin on this resistor, which had no input cap by the way, where the other end of that resistor went was already probably loaded down to ground with a resistor anyway, which is why the circuit worked perfectly in the guitar preamplifier but not on the breadboard. But it's only a simple modification to put a 22k, even a 100k resistor between pin 3 and ground, and we get a nice steady output. And I just looked that up. It's coming off of another OpAmp output from an inverting amplifier, so that would be used as a buffer anyway. That was the unbalanced output, and yeah, it would have been used as a low impedance source anyway, so it would have been setting the input impedance of the headphone amplifier correctly. Because it's not being used in this configuration, we have to add that impedance resistor there. But that's neither here nor there. We figured out the problem. I knew that and should have known that, but still made a mistake. Anyhow, that's what happens. I don't want to make this video too long about discussing and concepts and shit here. So what I might do is might put the camera on charge because the battery's going flat, and I'll hook it up to an actual pair of headphones, well, one channel anyway because I've only got one built, and just see what the output quality is like. It should be, according to the sweep test there, relatively good. So okay, I got the headphones connected to the amplifier, and we're looking at 1.1 volt peak to peak out, but it is fairly loud. That sounds so funny. Yeah, so anyway, it works. Now we go back into continuous mode. We can see from this roughly what we put in is what we're going to get out. So 1 volt in will equal 1 volt out into the headphones, which is average, and from where I'm standing, that 1 kilohertz tone is pretty loud, and I'm standing at least a meter away from the headphones. So I'm going to turn that off now because that's getting annoying. But yep, the circuit works. It's outputting nicely into a pair of headphones. It does the job. Don't think those transistors are getting hot. No, they're not. It works as it is. Just got to keep in mind we've got to add that 22k impedance resistor there between pin 3 and ground. So I'll end the video here with a final look at the schematic with the changes. Got a 1 microfarad capacitor on the input, a 1k still there, and between pin 3 and ground a 22k resistor. Anyhow, I've also got a 100 nanofarad capacitor across pins 8 and 4 of the IC as a high frequency bypass. So anyway, I'm the Astro 30, and if you enjoyed this video, please remember to rate, comment and subscribe below. And you can always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro saying, see ya, have a great day. And by the way, I will do a separate video explaining the mythical decibel measurement. See you later.